Hi everyone, this is section 9-3, tests for comparing proportions. So hypothesis tests for comparing two proportions. So in section 8-3, we compared two proportions using a confidence interval. So a confidence interval answers the question, what is the difference? And it provides an interval of possible values for that difference. A hypothesis test, on the other hand, just answers the question, is there a difference? Is one proportion more than the other? So when we do significance tests or hypothesis tests for a difference, we usually start by saying P1 minus P2, the difference between the two proportions. An observed difference between two sample proportions can reflect an actual difference in the parameters, or it may just be due to chance variation in the random sampling or random assignment to treatments. A significance test will help us decide which explanation makes more sense, but of course it does not give us a definitive answer. So our null hypothesis always starts with the assumption that there is no difference. So the difference P1 minus P2 would be equal to 0. Sometimes you might see this written as P1 equals P2. The alternative is that one of these three situations is true, that it's just not 0, so it could be more or less. We're not really sure which direction. Or we have a sense that P1 minus P2 is greater than 0, in which case this P1 would be greater than P2. Or P1 minus P2 is less than 0, where P2 would be greater than P1. The big difference here in this section is the standard error. The standard error is not calculated the same as it has been previously. This is the one and only time that we will see this. It is called pooling. So here's what's new. Our null hypothesis is that the two proportions are equal. So why would we use different estimates for each? We assume that they're the same. Think of our two samples as really just being part of one bigger sample in a combined population. Therefore, we will combine or pool the counts to get an estimate of the true population proportion. So this is probably the one and only time in your life where you will add numerators and denominators to add two fractions together. So the pooled population value is the sum of the two x1 plus x2, so those are our observed successes, if you will, and n1 plus n2, which are the sample sizes. Okay, so we end up with this. This is our pooled proportion, and then we use that to calculate the standard error of the pooled proportion. So whereas before we used P1 and P2, here we're using this pooled value for both fractions. Note the denominators are different. Here's N1 and N2. So here's an example. A study asked a random sample of adults about snoring. Of 995 respondents, 37% reported that they had snored at least a few nights a week during the past year. We split them into two age categories. 26% of the 184 people under age 30 reported snoring, compared with 39% of the 811 who were 30 and over. Is this 13% difference a real thing, or is it just due to natural variations in sampling? And pardon my typo on due, it should be D-U-E. All right, so how are we going to solve this problem? Well, first thing we're going to do is set up our hypotheses. So, in our state step, we want to state what we are trying to find. So I want to know if there's a difference in snoring between younger and older adults. Okay. My null hypothesis says there is no difference. The proportion of older people minus the proportion of younger people equals 0. My alternative would be, I think older people snore more. Okay. So the proportion of old minus the proportion of younger would be greater than 0. My next step is to plan. So if the conditions are met, I will use a two-sample z-test for a difference in proportions. So that is the formal name of the test. And what are those conditions? Well, same as they have been all along. Random, the subjects were randomly selected. 10%. We can assume that the number of adults in each group is less than 10% of all adults in each population. So note we're doing the 10% for each population, assuming that they're different in this case. Large counts, In the younger group, 48, so we had to do some math here to figure out that 48 of the group snored and 136 did not, because our 26% of 184 is where that came from. Okay, and in the other group, the older group, 318 snored and 493 did not. All of these numbers are greater than 10, so our conditions are met, therefore we can proceed. Next step. All right, so now there's a lot of steps here, a lot of things going on, and I'll show you a shortcut when we're finished. Okay, so first of all, our proportions, p hat for the young is 0.26, p hat for the older, 0.39, and that is based on our samples. Our pooled proportion, based on our samples, actually I'm thinking there should be a hat there, but okay, is we're going to add the numerators and add the denominators, and that will give us 0.3678. Standard error looks like this. So note we use the 0.3678, 1 minus 0.3678 for both numerators, and then the denominators are our sample sizes. And that gives us this number 0.039375. And our difference in our proportions is 0.39 minus 0.26, 13%. Next, we're going to find the z-value using this formula. So p1 hat minus p2 hat, we just said, was 0.13. Okay, minus 0, because again, we're assuming there's no difference in the populations. Standard error of pooled, we just calculated as 0.039375. When you do this math, we end up with 3.33. The probability that z is greater than 3.33 is equal to normal CDF. 3.33 is my lower, 1000 is my upper. I use 0 and 1 because I'm looking at a z distribution, which is the standard normal distribution, and that comes out to be 0.0004. The shortcut for all of this, you can skip all the steps we just did by using 2PROP-Z-test on the calculator, and there you put in your numbers. So you would have to calculate the number of younger people who snored out of all the younger people, the number of older people who snored out of all the older people, and we're assuming that P1, which is the younger, is less than P2. Now you could have switched these around if you put them in a different order. Then you would say P1 would be the older and P1 would be greater than P2. So you just have to pay attention to how you set it up. Conclusion. Since P equals 0.0004 is less than alpha equals 0.05, again, that was not given, so we had to assign that value, so we'll assume 0.05. We reject the null hypothesis in favor of the alternative. Older people do snore more than younger people. Notice how this is worded. This is called context. Older people snoring more than younger people. Okay, and just finally, inference for experiments. When you're doing experiments, you have a few other things to consider. Many important statistical results do come from randomized comparative experiments. Defining the parameters is a little bit more challenging because most experiments on people use recruited volunteers as subjects, so we're not randomly selecting people from the population. When the subjects are not randomly selected, we cannot generalize the results of the experiment to some larger populations of interest. However, we can draw cause and effect conclusions that apply to people like those who took part in the experiment. Unless the experimental units are randomly selected, we don't need to check the 10% condition when performing inference about an experiment. If you think about what's going on right now in the world with coronavirus testing, all of these things need to be considered when doing randomized experiments. And that takes us to the end of this section.